So we continue with Kirchhoff's voltage law. So in an electric circuit, voltages across the resistors, the voltage drops are always polarity respected. Okay, so they always have polarities opposite to the source of the voltage polarity. So in an example here, you can see that as the current moves around the circuit, you can see that polarity is observed. Positive, positive, negative, positive, negative, positive, negative, negative. So the current, in this case, is out of the positive side of the source and through the resistors, as indicated by the arrows. The current is into the positive side of each resistor and out of the negative side. The drop in every energy level across a resistor then creates a potential difference, or a voltage drop with a plus minus polarity in the direction of the current. And again, this will become important as we move on through our studies here, when we start looking at other types of analysis beyond and advanced to Ohm's law and Kirchhoff's voltage law. We still will use those, but this will form the basis. The voltage from point A to point B in the circuit then is the voltage source, and you can see that on either side of the battery. Also, the voltage from point A to B is the sum of the series resistor voltage drop. So you can look at it from the battery's perspective, or you can look out into the circuit from the resistor's perspective. Okay, so in looking at them then, the voltage from A to B, the sum of the series voltage drops, therefore the source voltage is equal to the sum of the voltage drops across R1, R2, and R3. So Kirchhoff's voltage law says the sum of all the voltage drops around a single closed path, in a circuit is equal to the total source voltage of that loop. So mathematically, how do we say that? Well, here's the mathematical way of saying that. V source is equal to the voltage drop V1 plus the voltage drop V2 plus the voltage drop V3 out to the nth voltage drop. If all voltage drops around a closed path then are added, and then this total is subtracted from the voltage source, and hence we get the net zero, the result zero as our relationship. So if we took V sub s and we subtracted V1, V2, V3, Vn, it would equal 0. Okay, so if we look at this here, the algebraic sum of all the sources, both source and drops, around the closed path then becomes 0. So it's just a summation. It just depends on how you set up the relationships. So the other way of stating it is as we see here, okay, as I just stated. You can see here what a voltage drop relationship actually looks like in terms of putting meters across the resistors. Okay, remember, current, you break the circuit and insert it, it goes through. Voltage, you go across each of the resistors. So 6.6 across this resistor, 5.4 across this resistor, and if you measure across both of them, you get 12 volts. Okay, so if we look at this simple example here, we've got a 5 volt R1, we've got a fuse, and we've got R2. Determine the source voltage where the 2 voltage drops are given. There's no voltage drop across the fuse, so that becomes negligible. It's a wire. So in this case, it becomes V source is equal to 5 volts dropped across R1, 10 volts dropped across R2, for a total of 15 volts dropped across the entire circuit. Okay, so as we move on here, you're going to see that the circuits become a little more complex. We're adding components. So in this case, we've got a 50 volt source. We know that we have a 10 milliamps of current flowing through, and we've got 1, 2, 3, 4 resistors, R1, R2, and R3 are shown here with values. R4 does not have a value. So they ask us to find the value of R4 based on what we've learned so far in our analysis. So maybe we're going to use Kirchhoff's voltage law to solve this type of relationship. So when we come back, we're going to go ahead and finish this problem and solve how we do that.